Alright, so today we begin a series on linear algebra, which is quite self-explanatory. Algebra of, or I guess you could say linear geometry, or I think before they used to call this course algebra geometry, but that's besides the point. Algeo, they used to call it algeo. I'm sorry, I'm getting off track already. But from what it seems, these are the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 main topics that they seem to have covered in the last 5 years on average. I guess sometimes they don't get this far, but this is what expectedly will show up on the exam. And for some reason, I guess we can keep this and we can check off as we go. And for some reason, the course actually starts at chapter 6. And chapter 6, if we check back here, it's called translations and rotations. Now, what it talks about first is rigid motion. So transformations in which distance between 2 points is still the same. Translation. And they talk about this rigid motion quite in depth. And he says, say, the translation of vector A which is equal to HK takes the point X, Y, and makes it so this is the transformed point X plus H and Y plus K. And that's pretty much what they mean by rigid motion. And this new point, I guess you could put it into new letters. We could call it P, U, and V. So point U, V. And we could take U and V, and we can further extrapolate that U is equal to X plus H, and V, I guess maybe I should put this, and V is equal to Y plus K. So let's just write a simple definition, as I've said before. Transformation in which distance is same. Now, the thing about linear algebra is that we must use examples to kind of encapsulate what's going on. Now, this is obviously easy. We can understand that it's something moving like this. So if this is the original line, this is a point on the line. The point on the line moves this way, and it's here, and it has the same slope on the line and everything, right? But once you get to harder topics, it's hard to encapsulate these without some sort of diagram or some sort of visual representation. And that brings us to the importance of making examples. So let's start off with an example to just get in the habit of making these things. Let's switch colors for examples. So examples from now on will be in black. So this is blue. I don't know if you can tell, but this is black. This is black. Oh, yeah, this is black, unless I am incorrect. So let's start off with an example here. So we have the basic formula of a line, ax plus by plus c is equal to 0. And the transformation we denoted by t is u is equal to x plus h, and v is equal to y plus k, like we did up here, right? And we can further extrapolate that x is equal to u minus h and y is equal to v minus k. This is basic algebra. And we can plug this back into this equation right here. A u minus h plus b v minus k plus c is equal to 0. And let's use distributive property. AU minus AH plus BV minus BK plus C is equal to 0. Now, what we can do is put it into AB form. So AU plus BV minus AH minus BK plus C is equal to 0. Sorry, this might be a bit messy. And from here, we know the slope is always negative a over b, right? So m is equal to negative a over b. And if we go back, the slope here is also negative a over b, right? Because it's u, v, h, k, sorry. This should have been k. A, u, u. Sorry, it's a bit hard to differentiate between the u and the v. I'll try to make it a bit easier because we'll be using a lot of u's and v's. But m is equal to negative a over b, and here m is equal to negative a over b. So when we know that slopes are the same, when this is the case, we know that lines are parallel, and this makes sense. Like in this example, right, the lines are parallel, or I tried to make them as parallel as possible. Let's move on to another example. So, let's say we actually add something that has actual values for slope, and it's just letters or variables that denote slope. So let's have m is equal to 2x plus 6. All right. Now, what's the slope here? The slope is 2 equals to m. Opposite way around, but yeah. And let's say that let's say that the transformation is 5, negative 1. So this is how we write the transformation. This is the notation, and it's important to remember this. So this is a is equal to hk, and you just add h and k to the x and y, and the changed point is x plus h and y plus k. So if you go back here, we can say that if we say if you find u and v off of this is u and this is v. I think this was a bit easier to differentiate here. we can say that u is equal to x plus 5, and v is equal to y minus 1. And then subsequently, we can say that x is equal to u minus 5, and y is equal to v plus 1. Right? Now let's plug this x, right, this x back into the equation. So if we plug it back and we plug y into the equation as well, we get y is equal to 2x plus 6. We know that y is equal to v plus 1. And we know that x is equal to u minus 5. And then we know that there's a plus 6 at the end here. So this is the equation. Let's do some simple. Plus 6. Distributive property, and then from here we can get 2u minus 4 is equal to v plus 1, and then v is equal to 2u minus 5. And then from here, we could bring everything to one side. 2u minus v minus 5 is equal to 0. And we know the slope is this over this. Or, for simplicity, we could also put it into v equals form. So negative v equals negative 2u plus 5. V equals 2u minus 5. Right. But that just goes back here. And basically this, you can find the slope, 2 over 1, m is equal to 2. And that means here, the lines are also parallel. So this just proves the former rigid motion law, right? And because here, the m equals to 2, and here m equals to 2, so the lines are parallel. Let's do another example. All right. So let's say we have the equation let's say we have and sorry, I guess we're not going to be doing anymore. The notes just stop here. But I guess that's it for today. It's been 12 minutes, and that is the first episode of Linear Algebra.